Okay, so what we want to do today is introduce you to our new topic. Basically, it is topic 2.1, which is looking at bonding and how different atoms are attracted towards one another. If we look at our periodic table, what you'll notice, and people have told me this morning already, the only set of elements on the periodic table that exist by themselves are the noble gases. And as people worked out, the reason why is they've all got a filled outer shell. So they've all got either 2 or 8 in the outer shell. What we are going to look at now really is our introduction to bonding. And so what I've said is that the driving force for bonding is that all elements are trying to achieve a full outer shell. And full means stable, essentially, in the world of atoms and electrons and molecules. And they can do that by one of two reasons. We would have seen this earlier in the year, where they lose electrons, or they can gain electrons. That's when we actually form things like ions. So we already know about sodium ions, and we already know about chloride ions. So in the case of a sodium ion, for example, a sodium ion would have lost an electron to get a filled outer shell, whereas a chloride ion has gained one. So if we looked at all the configurations that are possible, if it's got 2 in the outer shell, only one shell, then it's stable. If it's got 8 in the second shell, stable. 8 in the third shell, stable. 8 in the fourth shell, stable. So the driving force for everything is a full outer shell, right, as we just said. All right, what else do we need to know? Well, I've got on the board 3 different combinations of atoms. And the first one, hopefully, is fairly obvious. So if we're talking about metals, we are talking about a metal atom bonded to a metal atom. Funny enough, it's called metallic bonding. We have, or should have, some concept of a metal and what it might look like. And so what I've got here is an example of a metallic structure. So this is really just a whole lot of magnetic beads that are sort of obviously attracted towards one another, but it's a really good example of a metal. The reason being that these could all be, say, copper atoms, and we know that metals are malleable, so we can change their shape, and we can also take metals and we can actually, stretch them into pieces of wire. So this is a really good model of a metallic substance. But that would be like what you'd see under an electron microscope. We'll talk more about actually what holds the atoms together later. So that's our model like the metal there. The ionic compounds, as the name suggests, is an attraction for ions. And so ionic compounds are when we've got a metal bonded to a non-metal, but specifically they have to be ions. All right, so that's why they have got a charge. And so ionic bonding involves ions, but ions that come from metals and non-metals, or positively charged particles and negatively charged particles. And not always metal and non-metal, but we're going to use that scenario in this instance. What do they look like? Well, salts, as they're called, that's the general name for them, look like this. And so these are called a lattice structure, and not exactly perfect, this one, but the sodium's supposed to be the grey, and the yellow is supposed to be the chloride ion. If you can imagine this sort of going out in all dimensions, in all directions. So this is an example of a sodium chloride lattice. Funny enough, if you looked at salt underneath a microscope, you would also notice the crystals are cubic. And this gives you a bit of a hint as to why the salt crystals are actually a cubic structure as well. So we relate that back to crystal structure, but that's later on, a few years down the track. All right, so that's our ionic structure. The last one we want to look at is what we call covalent bonding. And covalent bonding is where we actually have a non-metal bonded to a non-metal. And the whole focus for covalent bonding is actually sharing of molecules. So here we've got the idea of sharing. So nothing actually loses or gains. That's why covalent molecules don't have a charge. They're all neutral. Over here though, in the ionic compound, there is a charge. So the formula for sodium chloride, for example, would be this. It is Na plus Cl minus. And of course we can drop the charge, but we'll talk more about ionic compounds later, but that's how we look at ionic compounds. And so over here, we have got sharing. Sharing really means overlap of electron clouds. So when the electron clouds overlap, the atom doesn't know where the electron comes from. It's not as if it's my electron or your electron. So the electron clouds overlap, if you can imagine that, in a real sense. And as they overlap, that's how you get a covalent bond. So every one share from each atom constitutes a covalent bond. So what we get from this perspective, okay, is molecules. And here's my beaker full of various types of molecules. So this will be a carbon dioxide molecule, for example, and carbon dioxide exists as individual molecules of carbon dioxide, okay, and the formula is CO2. Carbon non-metal, oxygen non-metal. Just so happens that there's two shared pairs here, that's why it's got a double bond. So that would be like carbon dioxide molecule, several of. If I had, for example, in this case here, if I use water as an example, H2O, here's my molecule of water. So water is a whole series of H2O molecules, okay, but individual structures, as you can see. So this is the concept that we want to get across about a molecular compound. And so, summing up, so you've got covalent compounds are metals, non-metals, straightforward, okay, and these form molecules, so these are individual structures, as you can see. Then we've got our ionic compounds. Ionic compounds are a lattice structure, and so these are a continuous structure. And lastly, we've got the idea of our metal, and metals are metal to metal bonding. That's what they're called, metals. And that's just our very brief introduction. Okay, oops, lost some of my metals. Come back. That's some of our brief introduction to our bonding